So the 10th lecture of this course, and we have seen a process mining from the exterior, I will call it, in the past few weeks. And so we have seen different types of operations that you can perform using process mining, automated process discovery, conformance checking, performance mining, variant analysis, even simulation, and how you can use simulation in conjunction with process mining to do what-if analysis based on the data you have. We also spoke a bit about how to prepare data sets to use them for process mining. And we talked about how can you use machine learning techniques in order to use the very same event logs you use for process mining, use them for building predictive models that allows you to predict, for example, for a given case in the process, how long it is going to take until that case completes. And I thought that in order to understand the limitations of process mining and to understand what can you do with process mining and what you cannot do and where kind of it stops, it's kind of important to also go a little bit inside process mining and look at the algorithms that process mining tools are using in order to construct the visualizations that are being displayed to you. So in essence, what I'm going to show you is what is a Promore doing or any other process mining tool doing when it builds this type of visualization, or what does it do to display this type of visualization? Like, for example, I'm going to take a process that has parallelism, like this one. And when a Promore finds, for example, that there is a choice here between this task or a parallel branch, how did it decide that there was a choice here and that here there was a parallel branch in here? How did it decide that here there is an OR gateway, etc.? What does it mean? And how much can I trust this process model? Or I'm gonna explain to you what goes under the hood, for example, when I take a process model. For example, here I have a process model of the production log, and I take the corresponding event log and I go and I animate it. So what is happening while this thing is like preparing? What is it doing? Why is it spending time? And then when you click on the play button, what are the tricks that the tool is using to determine where should a token flow from one place to another? Does a token needs to skip a task, or should it go through the task, etc.? All those nuances that go in an animation, you know. So let's go under the hood of what happens inside a process mining tool. I'm going to start by talking to you about how do we discover a BPMN model from an event log? And in particular, how do we decide that two tasks are in parallel based on the information that is available in the event log? And this is particularly tricky when we only have the end timestamp of each activity instance, which unfortunately is the most frequent case. If you go and extract event logs from a system like SAP or Oracle, you will see that you only get the end timestamp. You don't get to know exactly when the task started. You only end up knowing when it finished. And how can I infer parallelism in that context? And how can I distinguish parallelism from choices in the process? So there are a number of algorithms for discovering a BPMN model out of an event log. One of the simplest ones, and the one I'm gonna maybe spend quite a bit of time because you will be able to understand it and you can even like apply it yourself on a piece of paper, is the alpha miner. It's an algorithm that, you know, it's a very simple algorithm that tries to just look at the directly follows graphs and look at some relations in there, and bang, it tells you what gateways you need to place where. but it is very limited. And I'm going to show you some limitations of that algorithm. And then I'm going to introduce very briefly a couple of other algorithms, heuristics miner and inductive miner, and explain to you what they do and what are their limitations. And I'm going to then introduce you split miner, which is the algorithm for discovering BPMN models that is used inside Apromore. So the alpha algorithm is arguably one of the most basic algorithms for discovering a BPMN model out of an event log. It's an algorithm that takes as input, first and foremost, the directly follows graph. So we saw during the fourth lecture on automated process discovery, we saw the process map, and we even saw how you build one. You know, you take every trace and you start saying, if the trace tells me I go from A to B to C to D, I draw an arc from A to B, from B to C to C to C, from B to C, from C to D. If the next trace tells you I do A, B, C, E, then I go from A to B, from B to C, from C to E, and I create a new node for E. And I just keep repeating that for every trace, and I build a directly follows graph, or the process map, which is the type of the default visualization that a process mining tool gives you. There are no gateways in there. You cannot really figure out if there is parallelism, if there are repetitions, they get mixed up, and you cannot figure out where are the choices, because you cannot see if something is a choice or if sometimes it's repetition. So the alpha miner starts from that starting point and just takes the directly follows graph as input, and it basically tries to guess what gateways are there in between the boxes in the process map. And then it plugs gateways into it. And that way it turns the process map into a BPMN model. To do so, first, the alpha algorithm takes as input the direct succession relation, exactly the arcs in the directly follows graph, i.e. in the process map. So a direct succession relation tells me X greater than Y, tells me that in at least some cases in the process, X is directly followed by Y immediately after in a trace. From there, I can infer something called a causality relation. If I see that A is followed by B in some cases, and I never see B immediately followed by A, the alpha algorithm will guess that there is a causality from A to B. A causes B. For example, in the sepsis event log we have seen in previous lectures, there is a direct succession relation from emergency room registration to emergency room triage. And there is never the other way around. It's never the case that emergency room triage is followed by emergency room registration. Therefore, the alpha miner will deduce that emergency room registration causes emergency room triage. And you can imagine that from there, it will just draw an arc between the two, and it will put normally no gateway between them, unless it sees other things. What other things it can see? The alpha miner can also start trying to infer parallel relations. It tries to find, are two tasks in parallel? And then it makes this reasoning. If two tasks are in parallel, and bear in mind that I probably only know the end timestamps of each task, then in some cases, I will see B followed by C, and in some other cases, I will see C followed by D, because if B and C are in parallel, the intuition is that they are executed more or less at the same time, and therefore, sometimes B will finish a bit before C, and sometimes it will be the other way around. Task C will finish a bit before task B. So if alpha miner sees that there is a direct succession relation from B to C, and also the other way around, it says there is parallelism. And finally, if in some traces you see an activity X but you don't see an activity Y. While in other traces in the log, you see Y, but you do not see X. Or more specifically, if you never see X followed by Y, nor Y followed by X, then the alpha algorithm will just naively infer that these two activities are unrelated to each other. There is no relation between them. So from an event log like the one I'm showing here, this event log here, let me take a pen. From this event log, A, B, C, D, A, C, B, D, and E, F, the alpha algorithm that extracts all the direct succession relation. A is followed by B, B is followed by C, C is followed by D, A by C, C by B, etc. Then it sees that B is followed by C sometimes, and C is followed by B another time. Therefore, B and C are in parallel. That's what it says. Then C followed by B sometimes, and B followed by C other times, right? So C and B are in parallel. Well, this is exactly the same relation, just turn around. So this one is not very interesting. Then he says A is sometimes followed by B and never the other way around. So A causes B, same A causes C, B causes D, C causes D, and finally E causes F, because you never see F followed by E. The rest is unrelated. Having done that, then the alpha miner starts finding some patterns in that relation. So, I mean, from the log, it derives a number of relations: direct succession, causality, unrelated, and parallel. So from this event log, it deduces this. And it puts them in a matrix where the columns and the rows represents activity, A, B, C, D, E, and the same for the rows, A, B, C, D, E. And a cell in the matrix tells you what is the relation between the activity in the row, in this case D, and the activity in the column, in this case B. And here is telling you, for example, that B causes D, whereas this cell, let me choose a cell somewhere here. This cell is telling you that C is unrelated to E. There's no relation between the two. You never see C followed by E, nor do you see E followed by C. Now that I have identified these relations, then the alpha miner finds patterns in that matrix. If it finds that there is a causality relation between A and B, and there is nothing else, no other thing relating B to something else or A to something else, then it deduces that A and B are in sequence. However, if I see the pattern A causes B and A causes C, and I never see any relation between B and C, so what do I deduce? First, I execute A, and then I execute B or C, and these two have nothing to do with each other. It means probably that there is an XOR gateway in between. So after A, I can see either B or I can see C. And I never see B and C occurring one after another in any way. Conversely, if I see B causes D and C causes D, so two activities leading to the same activity, and these two activities, B and C, are unrelated, you never see them together right after the other, then you conclude that after B and C, there is a merge gateway, and then there is C. So you construct the pattern, the BPMN pattern shown on the top. So what remains to be known? Well, when do we have parallelism? Well, the alpha miner tells you we should put a parallel gateway in the process model if from a given activity A, it causes B, so meaning it's followed by B and never the other way around. It causes C, And B and C are in a parallel relation, meaning sometimes I see B followed by C, sometimes C followed by B. In that case, I'm going to say, hey, after A, there is a parallel gateway from which I go into B and C, and I do them in parallel. Sometimes B finishes before, sometimes C finishes before. And conversely, if I see that there is a relation, a causation from B to D and from C to D, and there is never, and these two activities, B and C, are in a parallel relation, they can finish in different orders, then I know that probably there is an AND join gateway before D, meaning that I synchronize. Sometimes I do B, then I do C, and then I continue with D, or I do C, then B, and then I continue with D. So 5 patterns in essence, and by repeatedly, I take an event log, I calculate the matrix with all the relations, and I put it there, and I start looking at all these patterns. I take a pattern and I see, can I find it? And I start with the parallel pattern, then the patterns for AND gateways, then the ones for XOR gateways, and then the one for sequence. And I just start finding if those patterns exist between a triplet of activities or not. If they exist, then I put the corresponding gateway in the BPMN model, and I keep iterating. So what do I see here? I see that A and B are in a parallel relation. And then I see that A causes B, A causes C, and B and C are in a parallel relation. So I will put a gateway, a parallel gateway after A. And then I keep iterating. I see that B causes D. I see that D causes C. C causes D. And then I see that B and C are in parallel, so I will put an AND gateway. And I keep recording these different things as I go through the matrix. And I keep putting the gateways into the model. And if I did that on a piece of paper, I will end up with this model here. After A, I have a parallel split. It goes into B and C. After B, I have D, and there is a synchronization right before. After D, I have two activities, F and G, no, E and F, and they are unrelated to each other. So there must be an XOR gateway before them and possibly an XOR gateway after them. And then the process finishes with F. So from the process map that did not have gateways, I extracted all these relations, and then I derived a process model with gateways by finding all these patterns. Let me show another example. And I'm going to explain it maybe now in a non-mathematical way, but rather in a very intuitive way. So I have A, B, C, D, E, F. A, G, H, D, F, E. A, B, C, D, E, F, E. A, G, H, D, E, F. And what do I see? Well, I see, of course, that the first activity is A. I'll put it here. The last activity is sometimes F, sometimes E, so I'm going to be a bit careful about it. After A, I see sometimes B, sometimes G, sometimes B, sometimes G. So, so I sometimes see B, and I sometimes see G. Interesting. So my question is, what gateway should I put in between? So sometimes after A, I see B, sometimes I see G. And do I have a relation between B and G? Actually not. I never see B and G related in any way. So I'll probably put an XOR gateway in here, because B and G are unrelated to each other. I never see them together, one after the other. After B, I always see C. and not the other way around. So most likely there is a relation here, and C is the only thing I see after B. That's important. I never see anything else after B than C, so there must be a directly follows relation. And after G, I see H. That's all I see after G. I never see anything else than H. Therefore, I'll put a sequential relation. Then after H, what do I see? D. Okay. Coincidentally, after C, I also see D. And C and H are unrelated. So C and H are unrelated. Yes, C and H are unrelated. Therefore, here I must have an XOR join gateway. And what happens after D? Well, sometimes there is E, or sometimes after D. No, after D there is E, but sometimes there is F. Sometimes E, sometimes F. Okay. So sometimes E, sometimes F. Now E and F are kind of in a relation themselves as well. E and F. But sometimes I see F followed by E and sometimes E followed by F. So what do I deduce? I deduce that after D, there is an AND gateway. Why? Because sometimes D is followed by E, other times it's followed by F, and E and F are in a parallel relation. As an additional trick, we can add a fake end event that I can call end of trace, end of trace, end of trace. This corresponds to the end event in my BPMN model. So this is the end event. And before the end, I sometimes see E, or I sometimes see F, and E and F are in a parallel relation. Therefore, just before the end event, I should have an AND join. And this is the model I get. So I introduce you first a little bit mathematically with the matrix and the patterns. But if you start playing it, you see it's very intuitive. So you are looking for your initial activity, and then you say, what can happen then? Is there only one possible activity that can happen? Then you just draw a line. If there are two activities that can happen or more, then you try to find a relation between them. Are these activities like in parallel in the sense that sometimes one finishes before the other, sometimes the other way around, or are they unrelated? And based on that, I decide whether I put an XOR gateway or an AND gateway. Now, the alpha miner is not an algorithm you would like your process mining tool to use in any way whatsoever, because it has a number of limitations. First of all, it makes an assumption that event log is complete, meaning that to discover a proper model, you need to have seen all the possible traces of your process. Well, that is unrealistic. As you have seen, processes are very complex. And even if I extract 1 million traces of an event from an execution engine, from an ERP system, it doesn't mean that there cannot be other ways of executing the process. The diversity of ways in which process can be executed is such that it is unlikely that at any given point in time, you have seen every possible case variant in your process. It's not possible. So just to give you an example, if I give you a log that contains these traces, A, B, C, D, E, A, D, B, C, E, A, B, D, C, E, and A, C, B, E. What do you gather? Well, I can see that it always starts with A, it always finishes with E, right? And in the middle, there is B, C, and D in different orders, B, C, D, D, B, C, B, D, C, C, B, D. CDB, sorry. And what do you conclude from there as a human being applying your intelligence is that probably B, C, and D are in a parallel relation. So the diagram you will draw will be A, and in parallel, you will have B, C, and E, and then B, C, and D, and then you finish with E. You synchronize and you finish with E. So that's what you would normally deduce, even though there are some possible orders between these activities that have not been observed. Yet the alpha miner will not be able to find it. I'm going to tell you why. Because you have seen B followed by C, but you have never seen C followed by B. Look, never C is immediately followed by B. Here is followed by D, but not by B. So the alpha miner will see, oh, C has never been followed by B. So B has been followed by C, but not the other way around. So it will not find that there is a parallel relation between B and C. Therefore, it will not put a plus gateway between B and C. Because all the rules it contains are very strict rules. You must have seen B followed by C and C followed by B to deduce a parallel branch. Another problem that the alpha algorithm has is that it is unable to do anything with self loops. Why? Because if you have a self loop, which means you do B many times, one right after another, you do like A followed by B, 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 then C. Let's imagine that. What do the alpha miner sees? It says that B is followed by B, and sometimes the other way around. Then in the worst case, it will be able to tell, in the best case, it can tell you, well, B and B are in parallel. But the alpha miner will only put each activity in one box. So it basically will do nothing with it. If you see A, B, 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 C, or you see A, B, C, as far as the alpha miner is concerned, these are the same processes. And it's not true. A process in which you only execute B once is very different from a process in which you may execute B 10 times. So the alpha miner does not have a rule for finding self loops, and it's not trivial to add it. Also, the alpha miner gets trapped in the limitations of process maps. A short loop, like C followed by B, and an R from C to B and an R from B to C, does not necessarily mean that B and C are repeated or in parallel. Sometimes it is parallelism, sometimes it is repetition. I have mentioned this on several occasions, that in a process map, these short loops, you have to be careful about them because sometimes they mean parallelism, sometimes they mean repetition. The alpha miner will always treat them as parallelism. Therefore, if you have a process where you have A, B, C, B, C, B, C, B, C, D, alpha, and then sometimes you see, so if you have that, alpha miner will say that B and C are in parallel. How stupid that is. Why? Because sometimes you see B followed by C, sometimes C followed by B, and there is a rule in the alpha miner that says when you see that pattern, it means these two tasks are in parallel. And yes, it's sometimes true, but in that particular case I gave you, it's not true. If I give you an event log that contains only one trace, and the trace looks like this, A, B, C, B, C, B, C, B, C, D, well, as a normal human being, you will say, hey, I mean, B and C are being repeated. There is a loop between them. You will not say B and C are in parallel. But the alpha miner will not be able to detect that. So what distinguishes when you have a short loop in a process map? How do you know whether this is parallelism or repetition? Well, one way is by looking at the frequencies. So if you see that, for example, in every case of the process, B occurs once and C occurs once in every case, only once, then you say, well, B and C cannot be repeated, right? They must be in parallel because they are only executed once per case. Each of these two activities is only executed once per case. So clearly, there is no repetition in there. So based on that observation, basically the observation is the following one. The alpha miner is forgetting about the frequencies. The alpha miner takes as input the matrix you are seeing in front of you. That's it. It never reasons in terms of how frequently different activities occur or how frequently A is followed by B and how frequently B is followed by C, etc. It just doesn't take that into account at all. So one way of lifting the restrictions of the alpha miner is by something called the heuristic miner. And the heuristic miner, what it does, it says, like, it's kind of clever. It says, look, the alpha miner does not look at the frequencies by which different activities follow each other. It only asks the question, is A followed by B at least once? Or is B followed by C at least once in the log? But it doesn't ask how many times. So the heuristics miner starts with that observation and takes as input a matrix of the frequency of direct succession relations. That is the frequency you see in the arcs in the process map. So it takes those as input. And from, for example, from this event log here, it will deduce that I see A immediately followed by B 11 times, 10 times in this case trace variant, and once in this trace variant. Or I see A followed by D 13 times, once in here, 2 times in here, and 10 times in here. And 10 plus 2 plus 1 is 13. By the way, this notation means that this case variant occurs 10 times in the log. So that's what the meaning of this superscript is that this trace variant occurs this number of times. So here A is followed by D 10 times, here is followed by D 2 times, here A is followed by D once. In total, A is followed by D 13 times. Then the alpha miner uses that matrix and some formula to assign to every pair of activities a causality index, is called. It's a number between -1 and +1. And 0 means that these two activities, say A and B, have a causality index of 0, will mean that these two activities are unrelated in the terminology of the alpha miner. If the causality index between A and B is 1, it means that always after A, the next thing I see is B, never anything else. And if the causality index is -1, it means that always A comes after B, roughly. And if it's in between, the closer it is to 1, the most likely it is that there is an arc from A to B. The closer it is to -1, the more likely it is that there is an arc from B to C. So now I can calculate a matrix of causality indexes. So a matrix of numbers between -1 and 0 out of my directly follows graph, effectively. And then for every pair of activities, I can write their causality index. So for example, from this event log you're seeing at the top, I derive the graph below, where, for example, there is a causal relation from A to B with an index of 0.92. There is a causal relation from A to D with an index of 0.93, etc. I then set a threshold. For example, look, every pair of activities that has a causality index below 0.8, between 0 and 0.8, or between 0 and -0.8, I will delete those arcs from this graph. Hence, I will only show you the strongest causality relations, and I will delete the rest. And if I do that, then I get the graph of the most frequent relations I see in the log. And in this case, from this graph, I can then start applying some heuristics. That's why it's called a heuristic miner, to find the gateways. For example, what do you think if after A, let's say intuitively, 92 times you see B, 92 times you see C, 93 times you see D, and you don't see things the other way around, right? So the intuition is that these three activities are equally likely to happen afterwards. And what do you deduce from that? Because this index, A, B, because you see this index here is close to 1, then I deduce that this activity happens, B happens after A in almost every case. 1 means in every case, 0.9 means in almost every case. The same thing, C happens after A in almost every case, and the same thing for D. So then in here, I'll probably put a plus gateway, because the causal relations between A, B, and C are very strong. If here I saw something like 0.3, 0.3, and 0.3, assuming that my threshold is not low enough, then I will probably put an XOR gateway, because like a third of the times I see B, a third there is C, a third there is D. So let me put an XOR split between them. In this case, I'll probably put AND gateways here and here. And therefore, I will approximate this process by saying that, well, there is A, then there is B, C, and D in parallel, and then there is E. And it's kind of true. Well, there are some exceptions here. There are some exceptions, but it's okay. So you can modulate this algorithm to make it more sensitive to parallelism or less sensitive to parallelism. And depending on how sensitive you make it, it will discover more AND gateways or more XOR gateways. So then you will get a process model, either with the alpha miner or with the heuristic miner or with another miner. And as you can see, these models are not going to be perfect for a good reason. You know, processes are very complex. And actually, you don't want a process that tries to capture every single pathway in your process. If you did, the process will be so large that you wouldn't be able to understand it. So one of the qualities we want to see in an automatically discovered process model is that it is simple. So you want a process model that describes your process with a reasonable size, with a reasonable level of structural complexity. You don't want a messy process. But you also want that your process is as accurate as possible. One measure of accuracy in the field of process mining is called fitness. Say your event log has 10 traces, A, B, C, D, E, A, C, D, B, E, etc., etc. You would like that if you take one of these traces and you start parsing it along the model, like I see A, oh, the model allows me to do A. Then I see B, oh yeah, the model allows me to do B. Then C, then D, that means that the trace was parsed by the model. I can replay the trace against the model perfectly. And you want the model to be able to replay, if possible, all the traces in the log. The ability for the model to replay all the traces in the log is fitness. A fitness of 1 means your model can replay all the traces in the log, and you are very happy. Your model explains every trace that has been observed in reality. However, it's never going to happen, because if you have a model that can replay all the traces of the model of the log, necessarily will be a super complex model when we are talking about real life logs. So fitness is the antagonist of simplicity. There is a way of balancing between the two. Yeah, one of them is by building models that can parse a lot of traces. You see, the more I have parallel relations in my model, the more traces it can generate. So if I put a lot of parallel relations, then I can generate any trace I want. But then my model is not going to be very precise. And precision refers to the fact that we want a model that can parse only the traces in the log and not some other traces. So if I put all the activities I see in my log in parallel, that process model can execute any combination of activities, can parse anything. but it's not going to be precise because it can generate a lot of traces. If you simulated it, you will be able to generate a lot of traces that have never been observed in the log. And I will show you an example of that in a minute. And finally, as we will see, you will like any event log is incomplete. So if I extract the event log with the case in the past 3 months, nothing excludes the possibility that there are some traces that could occur that have not been observed in the log. So I want a model that can parse the traces in the logs, that can explain what I see in the log, but that can also explain some other traces I have not seen in the log. So it is like in machine learning, you want the model to generalize. You want it to be able to, for example, tell you, this object I have previously seen is a flower, but you also want it that when it sees some other type of flower that it has never seen before, that it can say, oh yeah, this is a flower as well. So you want it to be able to generalize to certain types of flowers that you have not seen. So this is exactly what you want in a machine learning model. So it's the same from a business process model that you discover from a log. You want it to explain the traces that are in the log and to tell you, oh, this is a good trace. Oh, no, this is not a trace in the log. But you also want it to explain traces that are not in the log. The ability for the model to generalize, that's called generalization. Model that is perfectly fit is a model that can parse every trace in the log. A model that is perfectly precise is a model that can only generate the traces in the log. A model that generalizes is a model that can parse all the traces in the log, but also some traces that are not in the log. And you can see how generalization and precision are a little bit at odds, because precision tells you you should only parse the traces in the log, and generalization tells you, hey, you should also be able to parse some traces that are not in the log, but that belong to the process as well. And you want the process model to be as simple as possible. And these dimensions antagonize each other, as I will show you in some examples. So let me take this example. Coincidentally, in the field of process mining, the model you are seeing here is called a flower model. It's a model that can generate every possible trace consisting of the activities that are present in the model. In other words, with this model, I can generate every trace consisting of A, B, I, K, F, I, J, A, B, L, K, F, I, J. For example, let me give you a random trace. B, A, F, J, buff J. This model can generate it. Look at this. I can go here and I can do B. Then I can go here and then here. And then I can come back. And then I can do F. And then I can come back. And then I can do J, isn't it? And then I can come back. And then I forgot F, I guess. No, I already did it. BA. I think A is the one that I forgot before. Anyway, I'll do it. And then once I'm done, I finish. So I was able to parse the trace BAFG with this model. I can generate that trace if I simulate this model. And I can generate any trace consisting of these symbols. A, B, C, yeah, I can do it. A, B, F, G, yes, I can do it. A, B, F, 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 G, J, J, I can do it. I can generate any trace in the log. So this process model is perfectly fitting any log. You give me a log, it will parse all the traces in the log, like no problem, with 2 eyes closed. But it is very imprecise because it can generate many traces. It can tell you this is a trace of this process, this is a trace of this process, this is a trace of this process, for all sorts of traces that are rubbish, that have never been observed, and that do not resemble anything that has been observed. So we call this model is overfitting, underfitting. It underfits. It's too large relative to what has been observed. The model you are now seeing is a model that overfits the event log represented at the bottom of this slide. It contains exactly the traces in that log and nothing else. So, for example, in this model, I can generate the trace A, B, I, J, K, L, and I finish. Or A, B, G, J, K, I, L, and it finishes. But if there is a small variation, for example, imagine that in the real life, I will be able to see A, G, F, J, K, L. So this model will not be able to parse it, because if I go here, then I get stuck. I don't see G. If I go here, I don't see G. So it cannot parse this trace. So anything that is not in this event log at the bottom, this model just cannot parse it. So then this model has zero generalization power. It overfits the data. It describes exactly what is in the data, but if I give you another trace of that event, of that process that you have not seen before, then the model will tell you, hey, this is not a trace of this process, systematically, always. Therefore, it has zero generalization power. We call it overfitting. And ideally, you want something in between the first model I show you and the second one. Given the event log at the top, you will probably want a process model like the one at the bottom. And this process model can parse most of what you see here. After A, you can see B or F. Then you converge, you have G, and then you do in parallel I and J and K, and then L. Okay? It's not perfect. For example, in this trace, this model tells me that the traces should always finish with L, and it's not true. This trace does not finish with L, okay? But this trace only occurs 5 times out of 500 traces that are there. So then it's not very important. So then I'll say, like, fine, this model is not completely perfect, but it parses the vast majority of what is there in the log, and it also has it can even generate some traces that are not really seen in the log, but that are likely to be there in the process, that are likely to exist in the process because they resemble traces that are currently in the log. Every process mining algorithm will strike a trade-off between these 4 dimensions: fitness, precision, complexity, and also generalization, although I will not talk too much about generalization today. It turns out that the alpha miner in real logs is completely useless and nobody will use it. It makes too strong assumptions and it misses things that are very frequently occurring in practice. The heuristic miner and a variant of the heuristics miner called Fodena miner, they are viable algorithms. They generate models that have a high fitness and high precision, but they kind of go a little bit bananas when there is complex behavior. And sometimes they even produce models that are not semantically correct, that have deadlocks. So for example, given an event log of a real life process in an SAP system, this is what the heuristics miner discovers. In great part, because it's kind of finding patterns between pairs of activities, and that actually creates a lot of complexity in terms of the gateways that you can chain with each other. There is another algorithm called the inductive miner, which is kind of used by some process mining tools. So for example, PROM is a process mining tool that uses an inductive miner. And the inductive miner will produce models that are quite simple and nice looking. So visually very appealing, so low complexity. And these models can be very fitting. They can fit, they can parse all the traces in the log. But the inductive miner has one, let's say, fatal limitation, which is that very often in real life logs, it produces models that are highly imprecise, that can generate a lot of traces that are not in the model, because it uses some heuristics that when it cannot detect what is the pattern that relates multiple activities, it basically creates a flower structure between them. For example, this is what the inductive miner generates with with a real-life event log. We just changed the names of the activities. And you can see that this model can parse any combination of activities A, B, C, D, E, F, E. Let me give you an example. Let me give you A, B, E, E, D, A, followed by F, and that's it. So I just randomly put a string here. I'm going to try to rewrite it because it didn't come up very well. A, B, E, D, A, and then F, and J, sorry, and J as well at the end. How can it parse it? Look at this. It can say, like, I see A, sorry, it goes here first. In here, it can decide to go out or to go up. It goes up, it generates A, then it comes back here. It can decide where to go. So it goes here, does B, then it does C, then it comes back, then it does A again, and it comes back. So it parsed these 4 characters, then it did F, and then J. So it won. And I can create any sequence of activities involving A, B, C, D, E, 0, 1, or multiple times each of them, put them in any order, this model will be able to parse them. And that is because of some limitations that it has in terms of what types of structures it can discover. On the other hand, the models it discovers are block structure. So they are like, I can find blocks in the model, and they can be very nicely laid out. So an algorithm that takes some of the same ideas, but that relaxes the assumption that the models need to be block structure, is called the split miner. And this is the model you will discover from that same event log, from the same event log that generated the other models, the split miner. And here you see that I cannot generate any sequence involving A, B, C, D. You know, I can generate B and C, or I can generate A and E, etc., but I cannot generate anything I want. And how does the split miner works? First, from an event log, like all the other algorithms, the split miner discovers the directly follows graphs. And in the graph, it tries to isolate the loops. Based on that, it identifies the concurrency relations. It trims them off. Then it filters infrequent edges in the DFG. Then it discovered the split gateways, and that's why it's called split miner, because it discovers first the split gateways, and then it worries about discovering the joint gateways. So let me take an example. So I have on the left-hand side here a set of traces. The trace is described on the left, and the number of times that it occurs in the log is written on the right. Based on this event log, consisting of about 10 trace variants, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, each of which occurs 10 times, hence 100 traces, 10 case variants, each of them occurring 10 times, so 100 traces. Then it discovers the process map on the right. The thing I see on the right is a process map. It's a directly follows graph. The next thing it does is that it finds the short loops in the directly follows graph. And remember, a short loop can sometimes be repetition, sometimes parallelism. So what split miner does is that it kind of looks at how the cases transit through that short loop, and it sees if the short loop is sometimes taken, or if you always go one way or the other, but you never take the full short loop. So it tries to find out, do I ever see a trace that has BC followed by CB or vice versa? If it does, then this is probably repetition. If it doesn't, then it's probably parallelism. Having identified the short loops that correspond to parallel relations, it then deletes them from the directly follows graphs. So I obtain a pruned process graph. So I have deleted a lot of the edges, and I keep in my pocket the parallel relations. So I know that B is parallel with C, B is parallel with D, D is parallel with E, and E is parallel with G, based on the loops that I have seen in the original directly follows graph, the short loops I'm talking about. Then, to take into account the fact that trying to discover a process model out of an entire event log will give you to a big enchilada, a big spaghetti you cannot comprehend, then it applies a technique to remove some of the edges from the directly follows graph. So the most infrequent ones is a little bit like the arcs abstraction slider in a Promore. So it will say like, okay, let's take the edges that have the lowest frequency and let's remove them to make the model that I'm going to build a little bit simpler. And there is a threshold that tells me how many edges should I remove, or what is the frequency threshold for removing edges. It's kind of part of the algorithm. This directly follows graph, I rewrite it. I can treat it as a BPMN model that is lacking the gateway. So what I have so far is a BPMN model. So this is the same as this. It's a BPMN model that doesn't have gateways. So what split miner will do is that first it will identify the gateways. So I see here is that there is a task that has 3 outgoing arcs. So there must be a gateway afterwards. And based on the parallel relations it discovered before, it determines whether these things should be in parallel or they should be in sequence. Once it has found that this must be in parallel, then it finds, so it puts the parallel gateways, then it fills up the XOR gateways, and then you get a model that has split gateways, all sorts of split gateways like here, but does not have joint gateways. So the joint gateway is missing here, and the joint gateway is missing here. Then it puts an OR join in every join gateway. Just says, let's put an OR join. And then it has an algorithm. This is done. It's already a BPMN model, but split miner also has an additional algorithm, which is quite complicated. So I would not describe it, that tries to find which of these OR joins can be replaced with AND joins or XOR joins. So which ones are exclusive and which joins are parallel, based on an analysis of the process graph. And when it does so, then it can replace these gateways accordingly. In this particular case, for example, none of the two gateways can be replaced by an AND gateway or an XOR gateway, but sometimes it can happen. So I introduced algorithms for automated process discovery so far, and this is some of the big major central machinery that you will find inside a process mining tool, like a Promore or Celonis, etc. But there is a bunch of other operations on process models and event logs that require another very fundamental algorithm, which is log-to-model replay algorithms. A log-to-model replay algorithm is an algorithm that takes as input a process model, and I don't care where this process model comes from. It could be an automatically discovered process model, or it could be a manually discovered process model, one that I manually designed, or a combination of the both. I discover a process model, I edit it, and I get a hybrid model that has a bit automated parts and some parts that were manually designed. So I take a process model and I take an event log, and there are many process mining operations that requires to effectively replay a process model in an event log. Think about log animation, for example, when I animate an event log against a process model, what I'm doing is that I'm taking every trace in the log and I am replaying it against the process model, literally moving tokens to signal that this case is moving along the process. But replay is also needed for performance enhancement of process models. I'm going to show you what this means. Let me take, for example, the repair example. And let me open in the process discover and let me make it a BPMN model. Let me put a little bit more edges. And here it is, okay? So in here, after this plus gateway, or after this X gateway, a promoter needs to calculate how many times I execute this branch and how many times I execute that branch. After this XOR gateway, a promoter needs to know how many times I go this way and do a repair simple, and how many times I go this way and I do a repair complex and an informed user in parallel. So, and these are the numbers that go here, here, and here. These two numbers need to be calculated by effectively replaying the traces against this model and figuring out how many times we go this way, how many times we go that way. The same here, how many times we go this way, how many times we come from this direction, how many times we come from that direction. That is what's going to determine the numbers here. Replaying a trace against a model is quite trivial if the model is able to parse the trace. So let me start animating this process model to illustrate it to you. If replaying this trace against this model is quite trivial if after here I do either start or I do analyze defect. And after analyze defect, I do repair or test repair. But what is going to happen is that sometimes the trace cannot be perfectly parsed. Say after analyze defect, I don't see a repair complex. Normally, after analyze defect, I need to see repair complex. But you know, there are cases that after analyze defect, instead of repair complex, I will see repair simple. And this model does not allow it. It does not allow me that after analyze defect that there is a repair simple. It says after analyze defect, there is repair complex. So what do I do if a trace wants to go from here to here? So I need to infer that I need to skip repair complex so that and test repair. So I need to skip this task, I need to skip this task, and I need to make the token go around them and jump to this point so the repair simple can occur, then test repair can occur, then the end can occur. So when the animation engine replays a trace against the model and the next activity in the trace is not the one that is expected in the model, or vice versa, the next activity in the model does not occur in the log animator needs to figure out how can it correct for that discrepancy. Where should it move the token? Should it go one way or another? Which gateways it needs to traverse to be able to continue the animation of that trace against the model? This operation of replaying a model against a log is what it can be done using one of two families of algorithms. One of them is called token replay or token-based replay. The idea is I play the token semantics of BPMN. So in the start state, I am in the start event. Then I see A, and the model tells me that I should see A, so I'm happy. After A, I see B, so I move the token next to B. So I fire the AND gateway. After B, I see a C, so I move the token to the position after C. And then I see E, so I move the token to the next position, and then I have two tokens. I can fire the unjoined gateway and I can execute E, so everything is fine. This is a case where the trace I had here at the start can be perfectly replayed in the log. Very beautiful case. I see A, then I see B, and according to the model, this is perfectly okay. Then I see C, and according to the model, this is perfectly okay. And then I see E, and according to the model, this is perfectly okay. But what happens if you give me the trace ACE and you ask me, please replay it against this model? Well, A, that's good. I know what to do. I see C. Oh, I need to fire this, and then I need to execute C. And now I see E, and I'm going to tell you, oh, I really cannot execute E here. I should see a B first. Do you really haven't seen B? No, I haven't seen a B. So then I need to declare that there is a missing token, that there is a token missing in the yellow. This yellow token I'm showing here is missing. So I'm going to say, let me pop it up of my pocket and put it there. And let me make a note that I missed one token. Then I can do E, because with this token I popped up from the yellow token I popped up from my pocket plus the blue token that was already there in the other branch, I now can fire the plus gateway. Now I can fire E. And sorry to say, but there is a remaining token behind that got stuck, that didn't reach the end, whereas normally the token should reach the end. So I'm going to make a note that there is a remaining token. And in a way, what I am doing is like I am correcting for errors during the parsing. So if the next activity in the log is not what you expect in the model, I pop up tokens from my token to make it up, and I keep track of how many tokens I popped up. And this number of tokens I had to pop up, or number of tokens I left behind, is a measure of how badly the process model was able to parse the event log. There is another approach to this that requires a little bit more advanced algorithms, and that is called trace alignment. And trace alignment, what it does is that it's an algorithm that, given a process model and an event and a trace, is enough. If you have one trace, you can do it trace by trace. Given this trace A, D, B, E, H, and given this model, it will try to produce what we call an alignment. This is an alignment. And then the alignment tells you, okay, the first character can be parsed. So this is called a match. And you say, I see A in the model, in the trace, and I see A in the model, and I'm happy. Next, I need to parse D. So in the trace, I see C. And in the model, I can execute B or D. But what happens? In the model, there is no C. Normally, if D occurs, C should occur as well. But in the trace, I don't have it. So I'm going to say that in the model, I'm going to skip C. This symbol is called skip. In the log, I saw C. And in the model, I'm going to skip C. So I introduce this kind of error in here, saying like there is an error in the parsing of the trace against the model. And I'm going to correct it by saying that in the model, I need to skip this activity called C. Then I can match D against D. Then in the model, I have a B. And unfortunately, in the log, I have a D. In the trace, I have a B. And unfortunately, sorry to say, but there is no B in my model. Nowhere. I cannot find it. So I'm going to say that in the trace, when replaying the trace, I'm going to skip B in the trace. And I'm going to continue and read an E after that. So it's like I skip. I do as if this B didn't exist. That's what this means. Skip the B in the log. And then E can be matched. Yes. And then H can be matched. Yes. So I was able to build an alignment of this trace against this model that has only two errors. This is one error. And this is another error. These two skips. And essentially, the algorithm tries to explore many possible ways of aligning a trace to the model and then it selects the alignment that has the smallest number of errors. Or I can define some other cost function if I want, but the idea is I want the alignment that has the smallest number of errors. So given the above trace in this slide on the left and the model on the right, below I show you two possible alignments, two possible ways of parsing that trace against the model. The one below at the first of these alignments has two errors, two skips in there, and the second one has 10 errors, 10 skips. The one that has two errors has a lower cost, so that is the one that the algorithm will pick. In other words, the algorithm explores a number of possible alignments and then selects the one that has the smallest cost. And with that alignment, you can now replay the trace against the model, and you can know at every step what should you do if there is an error and you cannot parse the next symbol. It tells you, should you skip something in the model or should skip something in the log? And by following the alignment, you are now able to parse a trace against the model. And that is how log animation works. And that is how these statistics in the arcs in the BPMN model are computed. Now, computing optimal alignments is a bit expensive. So you will notice that a promoter does it in a bit of an approximate way. And all the process mining tools also do some approximations. So the numbers you will see in the frequency overlay in the BPMN model in a promoter are not perfect. They are approximations. And you should keep that in mind, that if you want to know how many times A is followed by B, don't try not to see that in the BPMN overlay, but try to see it in the process map overlay, because in the process map, the numbers are calculated directly from the log, and in the BPMN model, the numbers that you see are calculated through a replay operation that is not perfect because the error correction that a promoter is using is a bit approximate, it's not optimal. It doesn't lead to a minimum cost alignment. To recap, we have seen today algorithms for discovering process models from event logs, particularly the alpha algorithm, which is a very simple one. We briefly mentioned the heuristics miner and the inductive miner, which have different types of issues. And we also introduced the split miner in some details. So these algorithms try to strike different trade-offs between fitness, precision, and simplicity, and also generalization, which we left aside today. And once you have a BPMN model, and bear in mind that BPMN model is not a perfect reflection of the log, it does not necessarily parse all the traces in the log. In order to compute statistics on top of the process model, like overlays, waiting times, processing times, frequencies, etc., or to do animation, or to do model-to-log conformance checking, you need to be able to replay every trace in the log against a process model. And for that, there are two techniques: token-based replay, and then there is trace alignment, optimal trace alignment, which is a technique that is algorithmically more complex, but that computes the best possible way to parse each trace against the process model. And there is a bit of a, between token replay and optimal alignment, there is a trade-off of complexity. If you want to be able to handle very large event logs, then of course token-based replays performs better, is faster than trace alignment. So some tools will use token replay instead of optimal alignment. And that's what I want to talk to today. Two fundamental algorithms or algorithmic problems in process mining: automated process discovery and replaying a trace against a model when the trace does not perfectly fit the model, where sometimes the trace contradicts the model or vice versa, the model contradicts the trace. So that's what I wanted to tell today.